My name is Jianing Li. I'm currently the ECR Committee Secretary of Energy Storage Network Plus, and I'm also the chairperson of IEEE Power Energy Society UK and Ireland chapter. So welcome to today's event, and today's event is a joint event with Bioenergy, Offshore Renewable Energy, Energy Networks, Super Solar Hubs. The Supergen program is funded by EPSRC and was set up to deliver sustained and coordinated research on sustainable power generation and supply, focusing on several key research areas, including bioenergy, energy networks, energy storage, fuel cells, hydrogen, and other vectors. The event will be recorded. The preferred method for asking questions will be with the chat button that will appear at the bottom of your screen. Simply type your question using the button. If you'd like to ask your question verbally, with or without video, please press the raise hand button and we will try to connect you at the appropriate time during Q&A sessions. Okay, I'll give a very brief introduction about Supergen Energy Network Plus. The Supergen Energy Storage Network Plus is led by Professor Yulong Ding and University of Birmingham, along with the support of a multidisciplinary team of 19 investigators from 12 UK institutions, and it is funded by EPSRC. We have strong industrial support with 34 project partners and 2 million in-kind support. The Network Plus covers storage technology ranging from electrical, chemical, thermal, mechanical, and chemical, and storage-related areas such as energy storage and energy networks, energy and society, environmental, social, economical and policy considerations, artificial intelligence, and big data. The Energy Storage Network Plus aims to accelerate and support the interaction between those different sectors to deliver significant impact and research excellence, while supporting early career researchers and making sure that equality, diversity, and inclusion is an integral element across all fields. During the course of the grant, the Supergen Network Plus will identify key research barriers within the energy storage sectors funded to fund a number of feasibility studies through open competitive calls to the community. Activities so far, we've got dedicated funding to support research activities and personal development, opportunity to submit a paper for publication in the IET Smart Grid Journal, networking opportunities through dedicated events, Supergen Cross-Hub webinar series supporting the development of flexible funding proposal. And future ECR activity includes training sectors, ECR long-term industrial placements. And we have recently established the ECR committee within our network. You can click on the link. I'll circulate the link in the chat box so you can have a look. And thank you much. So I would like to welcome our first speaker, Mona Faraji Neera from University of Warwick. Her presentation is on machine learning for battery production, digitalization, smarter electrode manufacturing.
Hello everyone. Shall I share my screen? Hopefully you get it. Yes?
Yes, we can see it.
Perfect. Hello everyone, and thank you for joining my presentation. I'm Mona Farajiniri. I'm a PDRA for battery manufacturing and battery management systems and Warwick Manufacturing Group, University of Warwick. So my project is on machine learning for battery production digitalization, smarter electrode manufacturing. So this project is part of a bigger project called Nextro, which is a collaboration between 5 different universities, Faraday Institution, and a UK Battery Industry Research Centre. And the purpose is to move towards optimized battery manufacturing processes. The responsibility of WMG in this is building data science and machine learning models to understand how we can achieve the goal. So battery manufacturing process is made up of different steps, which is including the selection of the material, mixing those, coating and drying, calendaring, electrode cutting, assembly, filling electrolyte, and forming and testing. So this process includes a lot of steps and a lot of key parameters, like as the temperature, pressure of the environment, the settings of the equipment, and also all of this beside the uncertainties and the disturbances of the environment affect the quality of the final cells that has been made. So in a traditional battery manufacturing process, many of these parameters are being set by trial and error, but when we talk about the smarter battery manufacturing process, we want to make things more systematically and based on and providing suggestions based on the correlations that we extract through our studies. So machine learning is going to support this manufacturing optimization. So the purpose is to build models such that we can predict some of the critical features of the batteries, and this is supposed to help reduce the production cost, because if, for example, we can predict the some of the indices like as the capacity or the battery internal resistance before the manufacturing process is finished, so the cost of the experiment for getting that actual values can be reduced, because there won't be necessary to run those experiments. So these models, to build this machine learning models for manufacturing process of batteries, we start with the data sets that are coming from our own experiments in WMG. So we design experiments for that, and the data that we get are not obviously at their best format to be fed into our model. So what we do is we try to clear the data, prepare the data, and then we use this data to train our models, and they are normally in the form of multivariate regression models, artificial intelligence networks, and classification and clustering methods. And then based on that, we try to evaluate the outputs of the models and provide feedbacks and make decisions to improve the manufacturing process. Speaking about the steps, so we start with design of the experiments, which are based on the supersaturated design of experiments methods, which is based on the analysis of the variance to minimize the number of the experiments that can provide us high quality data. And then we go to build, to make our coatings for the manufacturing, because electrode is having the most expensive part of the manufacturing of the battery process. So we focus on that. We measure some of the features. We go to build our final cells and measure some of the indices like as capacity and internal resistance, and then we try to build a bridge via machine learning from the input factors to the output performance characteristics. So the data that we get, we start with the data preparation. We deal with the missing values, with the outliers, and with the noisy data, and then we extract features, and then we can input those features into our models, which are normally, as I mentioned, regression or artificial intelligence interpretable models, or normal neural networks, or other type of models. And then we try to predict the results and also do classifications and predictions. So what is still going on in this project is that we try to move towards more advanced AI models, interpretable AI models as well. We try to look at the problems, how we can extend the lab scale studies to normal industrial manufacturing scale, and also taking into account as many as key parameters that we can building these models. Thank you for listening. Happy to take any questions.
Okay, any questions? Oh, someone was asking whether we will be sharing this recording. Yes, we will be sharing the recording after the event. Actually, Mona, I've got a question for you. So
Yes.
It seems to me that the research is actually quite challenging and quite practical. I'm just wondering what is the biggest challenge that you think throughout the project?
Well, I think the quality as data I can't say is the main challenge. It's a challenge, obviously, because the most important challenge I can mention, the scalability from lab to the manufacturing line, because the quality of the equipments that we use for measurements and also the frequency of the measurements that we get inside our labs are quite high. So how those models can be robust to some kind of the size of the data, the quality of the data in a normal manufacturing line, I would say is the most important challenge in building those models.
Thank you. I've got two more questions for you from our chat. So Amruta was asking what platform were you using for the machine learning model development?
Well, it is right now. It is just MATLAB.
Okay, and James was saying that he saw you were studying the effect of calendaring on weight, and are you also looking at the effect on performance?
Well, yeah, we tried. Yeah, we have tried to correlate that once with the weight and the thickness, and then once with the performance. Yeah, we are trying to look at it as well.
Okay, thank you much. Thank you much for your presentation, and thank you
you.
much for the Q&A session. Thank you. So next, let's welcome James LaHoo from University of Southampton, and his presentation is on image-based modeling of electrochemical devices, linking structure to performance.
Everything working okay?
Yep.
Cool. The reason why I asked that question to Mona just then was because I thought maybe we could do a bit of collaboration if she was interested in see how that was going to affect the performance. So hi, my name's James LaHoo. Let me just get rid of. There we go. My name's James LaHoo. I've just started a postdoc at the Diamond Light Source, working at the diode beamline, which is the dual imaging and diffraction beamline. But that was from Monday, so this is all very new for me. Before that, I was working as a PhD student down at the University of Southampton as part of the CDT for energy storage and its applications. So I don't think we normally collaborate with Supergen, but we did a conference earlier in the year and people suggested that we should start talking to your group. So hopefully I'm the first of many people to come join. But we're a group of 50 PhD students looking at all different forms of energy storage, heat, batteries, compressed air and the like. And so the work I'm going to be talking about today is image-based modeling of electrochemical devices, so looking at batteries specifically. And the idea is that we're looking at to understand how the effect of the structure of these batteries influences the performance, so correlating that to some engineering properties. But just to widen this out to the rest of the group, these techniques can just be used for batteries. They could be also used for other engineering materials, so looking at maybe heat transfer or electrical conductions. And the like. So hopefully this is of relevance to the wider community as well. So just to start with a basic diagram of the lithium-ion battery, what we physically have is typically in a commercial cell, we have a multi-phase porous electrode. So we have a solid electrode structure with a liquid electrolyte, which acts as the ion carrier. And as we charge and discharge the battery, we physically shuttle these lithium ions between the cathode, the anode, and back. So physically, we have this transport problem going on. And when we think about how to understand this better as engineers and scientists, we can use modeling as a tool. And what I have here at the top right is just the wider multi-scale modeling framework around batteries, moving up the length scales. So at the atomistic level, we can use density functional theory to look at new chemistries. And at the grid scale level, we can use equivalent circuit models to understand it. But in this center area, what we want to be doing is understanding how this structure, looking at these 3D models, is going to influence the performance of these batteries. And so to do that, we can manufacture real electrodes and then use imaging techniques to obtain these 3D data sets. So when we take this to the synchrotron or to the lab-based X-ray tomography, we take our electrode sample, place it in a radiation source, and then fire radiation at it, obtain 2D projections on this detector, rotate the sample, and then we can reconstruct that into a 3D volume to obtain a representation of the microstructure of that material. So what's important to understand is these, typically at the lab scale, these are 1,000 by 1,000 pixels, or if we look at the synchrotron scale, they can be 4K by 4K detectors. So we're dealing with very large data sets and very large computational volumes. So when we think about imaging and combining that with simulation, it requires a lot of computational resource. So typically we use a process known as downsampling, where we reduce the resolution used, which then reduces the computational cost associated with it, but maybe gets us a bit further away from the reality. We can see we're closing off some of the pores in this case on the bottom right. So what my PhD was looking at, and this is my PhD in a slide, is to develop these techniques, these image-based modeling techniques, but to deal with these larger data sets. So if we look at a typical workflow of what I was up to, I was making lithium iron phosphate electrode here for a pouch cell. stick it in a CT scanner, obtain a 3D data set, post-process that into a two-phase segmented data set. We can see here the blue relates to the solid structure, the black is that porous phase where the electrolyte percolates through. And then we can use that as the computational domain to solve transport problems. So we can see here we've got a steady state diffusive flow in the X, Y, and Z directions. And we can start to use these techniques to inform our design. And the important thing about the software I developed, Open Impala, this is the logo for it here, is that it performs these calculations very quickly. So on the y-axis, we have time taken to perform the calculation, x, the number of computing cores used. And we can see that where a calculation previously would have taken us in the order of hours and days, we can do it in a matter of a couple of minutes. And this unlocks some really exciting science we can do. And this is why I'm at Diamond now. So the dual imaging and diffraction beamline, which is where I'm working, can obtain these operando images very quickly and obtain large amounts of data. And so what we want to do at Diamond is to provide a set of tools to the user of the beamline to give them some real simulation and engineering results. Instead of just turning up at home with hard drives full of terabytes of data, we can give them some real results. And hopefully this platform, this computational platform, can also unlock some other things. So understanding the effect of downsampling on those results obtained, this operando simulation stuff I was talking about here. Maybe we can start to use this as a platform to develop into further complicated multiphysics or looking at heat flows and electrical conduction. And also as a way to optimize these designs. Maybe this is something I can talk to Mona about, where we geometrically alter these image data sets, perform more simulations, try and obtain an optimized design, and then manufacture that design and see the effect that has on performance. So thank you very much for listening. Any questions? These are some papers from my PhD if anyone's got wants to look them up. And yeah, thank you very much.
Okay, thank you, James. Is there any questions? Any questions from our audience? Yeah, Navi was asking, how did you validate your model?
That's a good point. So this is part of there's a lot of different ways of measuring diffusion and tortuosity, which is the property I was looking at there. Experimentally, it becomes quite hard to measure those properties. So typically an experimental setup is doing something called mercury porosimetry, where you inject a liquid into that structure. That can be quite destructive, and you can obtain different results depending on the surface tension of that liquid. So when I was looking at validation of my model, I was comparing it to other simulation techniques. So there's stuff like pore network modeling, random walker techniques, finite element methods, finite differences methods. And yeah, we had some good correlation between some of those methods. I mean, there's a wide variety of results you can get for this. So yeah, definitely take it with a pinch of salt and understand that, yeah, that might be not fully representative of what's happening in reality. But I still think that's value.
Okay, I've got one more question. So Amarus was asking, can image-based modeling used for identifying and designing manufacturing process more compatible for future recycling?
For future recycling, I think that's an interesting question, because you'd be looking at how to, well, yeah, I think when you're looking at how to disassemble things, at the end of life, you need to be designing in features and how quickly you can crush them. I've done a previous project looking at recycling on alkaline batteries, but I think it becomes a bit trickier when you look at lithium-ion batteries. One of the problems is recovery of materials. So I guess you want to crush this thing into its constituent parts and then separate them out. So depending on the porosity of your material and the amount of steel used, that's going to affect how easy it is to crush these batteries end of life, I suppose. It maybe has more value in looking at manufacturing defects. So you could use these imaging techniques to see if you can see, say, islanding effects, delamination, gas formation, that kind of stuff in lithium-ion batteries. So yeah, maybe it does have a role to play.
Okay, thank you much, James. Next, I would like to welcome Katie Chong to introduce Bioenergy Hub, please.
Yeah, no problem. So I'm just going to share my screen. Let me get this right. Okay. So hopefully you can see the slides. Right, so my name is Katie Chong and I'm based at Aston University in, oh yeah,
Katie,
yeah.
We cannot.
You can't see?
No.
Oh dear.
Oh,
There we
That
go.
works?
Yep.
There we go. Okay, I hadn't quite pressed the button. Okay, so I'm Katie Chong. I'm based at Aston University in Birmingham, based at the EBRI, which is the Energy and Bioproducts Research Institute. And I'm part of the Supergen Bioenergy Hub. So we're interested in anything to do with sustainable bioenergy systems. So we're looking at anything that uses renewable resources like biomass and turns those into valuable vectors and into valuable products. So looking at biofuels and all that kind of stuff. So the way that the project is structured, our director is Professor Patricia Thornley. And we've got these different topic groups. So we've got a topic group that looks after resources. So Naveed is going to talk to you a little bit about biomass resources. Then we've got topic group 2, which looks after pre-treatment and conversion. So how can we turn those biomass resources into useful stuff? So into things like hydrogen, into things like biofuels, biodiesel, bio-oil, all of that kind of stuff. Then we've got topic group 3, which is vectors, that looks into how we can use those vectors and how they can be integrated into the existing infrastructure. And covering all of that, looking at the whole system, is topic group 4, which looks at systems. So taking the systems as a whole, looking at how they can integrate, how they perform as a whole. So we do a lot of integration within the hub with industry, policy and society. And one of the big things that we do is ECR training. So we've got a network called the Share Network. Naveed has just recently come on board to be part of the committee of the Share Network. So we run lots of different events to help support our early career researchers. So that's it really in summary. I'll put the link to the website into the chat. And I'll want to introduce you now to 2 of our ECRs within Supergen. So first up, we have Naveed, who is based at Aberystwyth University, and he's going to talk to you about resources. So his stuff comes within topic group 1. So over to you, Naveed.
Thank you, Katie. Let me share my screen. I think now everyone can see my slides. All right. Hello, everyone. My name is Naveed, and I'm a special modeler in Aberystwyth University. And today I'm going to talk about resources overview and potential areas for bioenergy crops. In our topic research group resources, as Katie introduced about different topic groups, and I'm part of the first topic group, which is resources, and which is being led by Ian Donison. And also Rebecca is part of our topic group. She's from CEH. And we are working on researching and developing the production and potential of different biomass and waste feedstock. What are the different options for the production of different feedstock that can be efficient and available to meet our energy requirement for the country without any negative impact of food production and maximize our environmental impacts and global climate benefits. There are different research questions. The first of the research question is how we can grow biomass on low-grade marginal land, and can get crops for more resilient to extreme climate events, and how we can deliver ecosystem services. Either is there possibility to have energy crops which are where the cost of that production, we can reduce it, how we can reduce the cost of production, and how we can increase our yield, and also how to match our end user requirement, keeping in view different other environment and ecosystem services. When you talk about bioenergy, it starts from anything from electricity and gas generated from organic matter, which is known as biomass, and the transport fuels are animal materials or any of the bioproducts and municipal waste to produce biofuel, oil crops for biodiesel, and sugar-rich crops for bioethanol production. And the resources are anything from plant and timber to agriculture, food waste, and research. So agriculture system is a whole system. It starts from sowing towards harvesting, and there are a lot of different phenomena, environmental and ecological phenomena going on in the field. But there are different challenges, and one of the challenges is climate change and the future climate, and the second challenge is land availability to grow bioenergy crops because of food security, to keep and maintain the food security. And also there is economic uncertainty. So all these challenges, how we can meet. And then there is a question arise on availability of the land for these bioenergy crops. And one of the options is a marginal land, but there is a different concept for marginal land. And it depends on a different area, because it's very broad term, and in different areas the definition of the marginal land is different, and it depends on the time, space, and discipline, and how we are going, because some of the lands are marginal at one point and one place, but for one purpose, but for other purposes that may not be the marginal land. There are different types of constraints and challenges to our agriculture, which include the climate constraints, geophysical constraints, socio-ecological constraints and challenges, and economic challenges. And all these define any land as a marginal land or a productive land. So how we can go and which crop can perform better on these marginal lands. And one of the options is miscanthus, because the research studies shows that on marginal land where the other crops produce less output, but miscanthus is a crop which is a very efficient type of bioenergy crop. It's annual grass. It grows very well on these marginal land. And to identify where we can grow those marginal land, what are the potential areas to grow these type of bioenergy crops on marginal land or other type of productive land. So MISCAN4 is a model which is Fortran-based model, and it is actually a process-based model, which is a modified form of MISCAN model. And it processed different light interception by the canopy, and it worked on that. And behind there are a lot of different equations which run and that characterize different functions of the biological system. Using that MISCAN4 model as a crop model to identify the potential areas of in UK. So we use this model, which has additional functions of thermal time, temperature dependent, radiation use efficiency, drought and frost kill predictions. A lot of different options has been made. And we have recently modified this MISCAN4 model to a biogrow model, which also include the other types of crops, not only bioenergy crops, but the other crops as well. But I'm using this MISCAN4 model for bioenergy crops, including miscanthus, ryegrass, red and white, clover, oats, and cereals as well. Here was a list of dataset and resources, sources which I have used to run the model, and these are input dataset starting from the climate data from Met Office, UKCP 09 and UKCP 18 data for current and future climate data I have acquired from Met Office, soil data from EASA, and crop data from Aberystwyth University for different types of crops, land use and land cover data from Food and Agriculture Organization of United Nations, and database of Welsh government, and admin boundaries from ONS. So using that dataset, I have developed a methodology starting from using the field experimental data to calibrate my model, and that include the crop data, soil data, weather data for the crop season. I have calibrated my model, and after when the model was well calibrated and it shows a very good result from statistical side, then I use that on a spatial scale for overall in Wales to see how the model perform on a larger scale. using the graded weather data and graded soil data from EASA and Met Office data from graded weather data from Met Office. So after that, I have done using that data set in different layers, and I use it in the MISCAN4 model, and then I did validation from using different statistical indices of RMSI, root mean square error, model efficiency model, and different other type, R-square, D-stat, and all these type of different statistical tools I have used to validate my model. And after that, I developed some potential areas for miscanthus, ryegrass, and oats, and also for willow as well, because that's also a really good bioenergy crop for the future. So potential areas for current scenarios and potential areas for future scenarios, how what are the resources availability, sites available, and the hotspots available to get to meet our energy requirement. And the next is landscape decision making and long-term strategy development, and that involved my model parameterization, high resolution mapping, and after validation, filter out some of the areas which are not the true type, or outliers removed, and then ground truthing from those areas to identify where are the hotspot in overall in UK where we can get maximum benefit and maximum utilize our land for our bioenergy production. And the second and the last
I think we are running a
yes, that's the last slide.
Okay,
it's
thank you.
Organic waste prediction model, and that's I'm about to develop using the organic waste data from different counties and waste collection organizations. I'm using the data set from those companies to see how we can predict the organic waste availability and what time those organic wastes are available to our to meet our energy requirement. Thank you.
Thank you very much, Naveed. Does anyone have any questions? No, not at the moment. So I'll ask a quick question. So for those people that aren't in bioenergy world, who is this information useful for? Who is going to use this information?
Yeah, that's a really good question. All right, so the whole work is not only about, because it looks like it's only about policymakers, because it can help to our industry people as well, because for our industries who are working on energy system development and on manufacturing side, are those who are in waste management and from that side energy production. So this is very helpful information for those people, especially from the organic waste model and also from the areas available for bioenergy crops. And also this information is helpful for our policy makers, government officials, to develop long-term strategies to meet our energy requirement. And the third is, this information is for our farmers, who is also the good means the main stakeholders, to decide what they can grow in their land based on their land, soil, climate, and water availability data.
Brilliant, thank you, Naveed. There's another question for you in the chat there, but I'm conscious we're running out of time a little bit, so I'm going to move on now to our next speaker. But Naveed, if you could just answer that question in the chat for me, please. So moving on now to Shuming, who is from Queen's University in Belfast, and Shuming is working on a conversion technique, so we'll tell you about biomass gasification. So Shuming, over to you.
Okay, can you see my screen now?
Yes, we can see it, thank you.
Okay, so good morning, everyone. I'm Shuming Zhang from Queen's University of Belfast. I'm a second-year PhD student, and it's my pleasure today to give a presentation of my recent research to our colleagues. So the topic is energy-efficient biomass to syngas conversion via autothermal calcium oxide looping biomass gasification. As is known to all, climate change due to CO2 emission has created an increasingly urgent demand for sustainable energy production technologies. Biomass gasification has been regarded as a renewable technology to produce syngas for energy generation and valuable chemical products. However, traditional biomass gasification has several problems such as low process energy efficiency and syngas quality, CO2 emission, and ash sintering as well. In order to improve the performance of for scale up of traditional biomass gasification, custom looping biomass gasification has been proposed and investigated by many researchers. As you can see from this graph, the mechanism of this technology is to utilize calcium oxide as biomaterials to capture CO2 in order to move forward the equilibrium of multi-reactions during gasification, and especially water gas shape reaction to get a hydrogen-rich syngas. However, it has several problems such as calcium oxide-based solvent deactivation and deactivation and biomass ash agglomeration. So in order to solve this problem, our research group who firstly proposed a concept named autothermal calcium oxide looping biomass gasification. And we are more focusing on the thermal property of calcium oxide. We utilize calcium oxide carbonation heat to provide energy to reduce the running gasification temperature in order to get a higher energy efficiency. So for today's presentation, I'll introduce about the energy assessment of calcium oxide carbonation heat as energy supply for biomass gasification. So a little bit of our previous work, we achieved threefold CO production improvement, and higher syngas yield can be obtained by lower gasification temperature. So in this case, we use the power off mode, which means that because reactor power always has the influence of the temperature of gasification, so we use the power off mode. After reaching the set temperature, for example, 650 degrees, and then we shut down reactor power to see the possibility of calcium oxide carbonation to supply the gasification process. And in order to observe this phenomena, we insert a thermocouple to observe the temperature difference. So from the offline GC results, basically we've got a similar result with our previous work. With the increase of calcium oxide to biomass ratio, syngas yield increased. So in order to study further this result, we investigate from three perspectives. The first one is to investigate the online syngas production tendency while recording the reactor temperature. The second one is to investigate the process endothermic and exothermic difference by DSC analysis. And the last one is to quantify process energy saving by Osborne simulation. So from the results, we can see that compared with traditional biomass gasification, our process, most of the CO2 was converted into syngas products. And what's more interesting is that after shut down the reactor power, the final reactor temperature difference is showed it around 20-degree difference, confirms that the heat released from calcium oxide carbonation was used to support biomass gasification. And I also did some comparison work under different holding temps. From the results, we can see that after holding for 10 minutes at the optimized temperature, there's almost no final reactor temperature difference because most of the calcium oxide is converted to calcium carbonate, which is reasonable. So in order to calculate the conversion from biomass to syngas, the TGA showed it a known result that the weight of solid residue both influenced by biomass degradation and calcium oxide carbonation, which make it difficult to calculate the conversion because we can't simply compare the weight of solid residue before and after gasification. So in order to solve this, I collect the solid residue and did the TGA and the nitrogen atmosphere, and we know the percentage of CO desorption, and the released gaseous components was detected by FDIR and confirmed is CO2. And based on the provide equation, we can know and calculate the conversion, and we achieved a significant conversion enhancement from around 30% to 86%. So the second section is the DSC analysis. From the first figure, we can see there's endothermic peak and exothermic peak separately for per cellulose and per calcium oxide under flue gas atmosphere. And as you can see from figure B, compared with traditional biomass gasification and the nitrogen atmosphere, our process can achieve a smaller endothermic peak, which fundamentally proves that the heat released from calcium oxide carbonation can reduce energy required for biomass gasification. So for the Aspen simulation, as you can see from this flow sheet, we used no heat duty mode for gasifier, and all the materials input was set as room temperature. By modifying the energy input to the process, we've got a relationship between process energy input and reactor power by Aspen sensitivity analysis. As shown in this figure, we can see that the black line is the traditional biomass gasification. In order to achieve 600 degree gasification temperature, the required energy input is around 6 kilowatts. But with the increase of calcium oxide to biomass ratio, the required energy become less and less. And our process can provide maximum around 2.7 kilowatt per kg per hour biomass mass flow. So from the simulation results, as shown in these two tables, higher syngas yield and conversion can be obtained by same energy input, and similar syngas yield can be obtained by lower energy input, which is consistent with our innovation. So to summarize, the DSC analysis fundamentally proves that the released heat from calcium oxide carbonation reduces the required energy for biomass degradation. Aspen simulation results show that our process can save around 1.8 kilowatt energy per kg per hour biomass mass flow in a practical application. And our process achieves significant syngas quality and conversion enhancement. And thanks for the supervision from Dr. Chunfei Wu and the help from Hebei University of Technology and Xianjiao University and the URES project. That's all. Any questions?
Brilliant. Thank you, Shiming. Interesting work that you're doing there, looking at gasification. Right, so you've had a question from John Harwell. So he's asking, can you use this method as a way to convert waste polymers, e.g. polythene bags, into syngas as well? Would be a great way to make plastic disposal economical.
Yeah, of course, because we are focusing on the calcium oxide carbonation heat as energy supply. So for the wet biomass is the same. Yeah.
So I'm going to jump in here a little bit and say it depends. It depends because it depends on what type of reactor you've got as well. So fluidized beds really don't like plastic because as soon as you add any kind of plastic to a fluidized bed, what happens is it melts and then you just get a massive clump in your fluidized bed, and so you can break your reactor. So if you're going to use plastics, you need to think about a slightly different technology maybe than a fluidized bed gasifier. But yeah, gasification of plastic is a real potential, and there's lots of work going on around that.
Yeah.
Any other questions? No, brilliant. So thank you very much to my two speakers from Bioenergy, Naveed, Shiming, brilliant job. And I will now pass over to Lindsay, or is it Lindsay? Are you doing the handover?
I think it's Kumar Debnas.
Oh, Kumar's doing it. Okay, thank you.
Yes.
Yeah, I'm going to share my screen first. Where is that? I hope everyone can see me.
Yep.
Yeah, all good.
Cool, thank you. Hi everyone, I'm Kumar Debnath. I'm from Harriet University. First, I'm going to give a brief introduction to Supergen Energy Network, and then I'm going to present my work in a very fast pace, I guess. So the Supergen Energy Network is comprised of 6 leading universities, as you can see, and we have 30 industrial and more than 27 university, national and international collaborations. Network-centric, multidisciplinary, and whole system approach is the target for this group. And we have 3 working groups, which works at the energy network architecture, climate adaptation and mitigation, and market and regulation. And as you can see, we have quite a lot of industry partners here. So the strong focus of equality, diversity, and inclusion is in the energy networks, and recently led on a cross-hub survey addressing the impact of COVID-19 and the research across the hubs. Taking into account the feedbacks from past surveys, we ensured the meeting and webinars are held between 10 a.m. and 3:30 p.m. and not over the lunchtime, and all webinars are added to the website to enable colleagues to view at their own convenience, and the speakers and or chairs are diverse and inclusive too. And we are also looking into greatly supporting the ECRs, SeedCon Fund, to help ECRs to develop new research ideas within the remit of the hub and to help advance career development through the community, have enabled several introduction and to industrial partners for future funding application or secondments, and providing letter of support to help with future fundings. Recently awarded 6 ECR SeedCon Fund funded projects, funded 10 research projects through Flexible Fund, which one of them is my work, which is going to be present later, and currently working with Offshore and Storage Plus to award across hub funded projects. And these are the contact information if you want to contact our group. So now on to my work. First, I'm going to talk about that, what's the motivation behind the project, and then I'll go towards the methodology and findings. So when we look at the total CO2 carbon emission in the world, by 2005, we can see that middle-income countries are emitting more than the high-income countries, and by 2008, the upper middle income also crossed the high-income countries. So right now, even if the high-income countries are lowering their emission because of the increase of emissions in middle-income, lower income, high income, and upper middle income, the world emission is still going up. So in the future, if we don't look into developing economies to reduce, to decarbonize and reduce their energy-related emissions, the world emission is not going to reduce. It may actually jump up again, and we are going to run into the same problem that happened in the past in high-income countries are going to run again in the middle and upper middle and lower income countries. From that point of view, we started this project where we wanted to see that what's the possibility of decarbonizing a country by actually creating a regional collaboration, energy collaboration. And our targeted area was South Asian countries of Nepal, Bhutan, Bangladesh, and India. And the targeted country which we wanted to decarbonize was Bangladesh. And to give you an overview of Bangladesh, it's half of the size of UK. And if you put 1,239 people per square kilometers, that's the Bangladesh. Bangladesh has the highest per square kilometer density in the world, and due to sea level rise, Bangladesh may lose from 10 to 25% of its land mass by 1.5 meter rise of the sea level. So a country that is going to be highly affected by sea level rise is planning by 2041 to convert their highly gas-dependent electricity generation, which is 68% in 2015, as you can see here, to 2041 to alter it to 55% coal-based, largely due to the need of affordable and high energy demand due to manufacturing industry, and especially the ready-made garments industry. I can assume that every one of you may have 1 or 2 garments made in Bangladesh in your closets, which is very common in the UK. So in that situation, if we look at the surrounding countries, India has a 71% coal dependency of electricity generation, which is very high, and they are also trying to decarbonize it. But on the other hand, Nepal and Bhutan, they are one of the highest they have one of the highest potential of hydro, and they are 99.9, almost 9% to 99.6% in case of Nepal is coming from hydro. So we wanted to see that, is it possible that how much of the electricity in the future that is depending on coal can be replaced with the import from hydroelectricity from Nepal and Bhutan, which is targeted towards 6,000 megawatt by 2041, which is just 10% of the total generation by that time for Bangladesh. And we developed a two separate country models, Nepal 2050 and Bhutan 2050 models. And we already had India and Bangladesh's 2050 model, which we incorporated these four models into a regional model to actually check that how, after meeting the demand in Nepal and Bhutan and India, how much of the renewable energy generated can be exported and help in decarbonizing the Bangladesh's economy need of electricity. And these are the 6 scenarios. For example, we have checked in this one case where Nepal and Bhutan is going to supply the majority of hydropower, and also in addition to solar and wind also. And as you can see, that hydropower is the primary support here. Our results show that if there is nothing we intervene in Bangladesh, the GHG emission will rise in Bangladesh up to 508 million ton CO2 equivalent, which is lower than 2015's France, which is higher than 2050's France's emission, which is around 470 million ton. So you can imagine Bangladesh by 2050 is going to emit more than France in 2015. And we tried to see that how much we can decarbonize, and our results show very good promising results where Bangladesh can decarbonize the entire coal and oil-based generation by 2050. And that will lead to the emission to limit the emission to 171, which is supposedly can go up to 508 million ton. So our result shows that this through this model, it is feasible for Bangladesh to replace its planned oil and coal power generation by 2050 by importing renewable energy from Nepal and Bhutan. Also, it can reduce 90% of its all fossil fuel based generation capacity by 2050. And by doing that, Bangladesh can reduce 66 to 83% of the projected GHG emission. Now, such a cross-boundary energy collaboration always comes with a lot of challenges. One of the biggest challenges is the geopolitical issue, which you can see that China is also involved because of the river location of these hydropower plants. The intermittency of hydro and solar and wind is also another issue that we need to look into. There are possibilities that these hydropower plants in Nepal and Bhutan can also act as hydro batteries for this region if there is a collaborative energy market can be established. There is energy dependency. No one country wants to depend on another country for their energy, but if it's a good deal for Bangladesh and Nepal and Bhutan and India, and also it helps to decarbonize this vast populated area. 20% of the population lives in this area of the world. And financing is another massive issue here. Environmental impact of hydropower plants would be another great issue, and as well as climate change, which is going to also change the potential of hydrogen energy. Our future scope of this model is vast. We can use this type of modeling to even evaluate that how Kazakhstan, which is a 90% coal and gas dependent country, can use the 95% hydro dependent Tajikistan and Kyrgyzstan neighboring countries energy to decarbonize their energy generation. On the other hand, a similar situation where Malaysia and Indonesia has a highly significant solar potential due to geolocation can help to decarbonize their own, as well as Singapore's 95% natural gas-based power generation. So this type of energy collaboration in the different parts of the world where neighboring countries have higher renewable potential can actually help countries which are which are lower in renewable potential to decarbonize their energy generation. Thank you. Any questions?
Okay, I've got Amruta. So what are the challenges in renewable generation instead of coal-based generation in Bangladesh, supplementing import from Nepal or Bhutan?
The major challenge is definitely the geopolitical and also the environmental issue. Geopolitically, which I already showed here, that China is involved here, and it's the same river is crossing through 2-3 borders. So if you put a hydro plant in the upper stream, what happens to the lower stream is one of the biggest questions, and also the environmental impact would be quite huge. And so if we can go through this, because recently India developed India updated their regulation towards in Nepal and Bhutan using their electricity line to export electricity in Bangladesh. In 2018 this happened, and after that Bangladesh also already in talks with Nepal and Bhutan to import the energy, but there wasn't any model to show that how much we can decarbonize with that sort of procedure. And now we know that what is the potential from Nepal and Bhutan, and also how much we can decarbonize in Bangladesh.
Okay, there's another question from John. So similar to the above, why do the countries need to import hydropower from neighboring countries? Could they not produce hydro locally?
That's a very good question. Thank you. The main problem with Bangladesh is that Bangladesh is a very flat country. The hydro generation capability for a country depends on the geographical terrain. You need mountains, or at least like up and down streams where you can actually put the hydropower plant. Bangladesh has one hydropower plant which caused a severe environmental impact, and it is just 250 megawatt power. And that's why Bangladesh is putting their emphasis on future generation through coal, because their gas is depleting, and by 2030 to 40 the gas will be totally depleted. So then what Bangladesh is doing, they're investing in coal, which coal is also imported. So I think that when you are talking about importing coal and generating electricity, which you can also do by investing in Nepal and Bhutan, which India is already investing in Bhutan for getting from one power plant, which Bangladesh can do in Nepal and Bhutan, and import that hydro energy. So both of them are importing. So I think it's more sustainable if we go towards this type of hydro generation rather than coal generation.
Okay, thank you much for the presentation, Kuma. Next, we would like to welcome Matthias Noble from University of Manchester for the presentation of bridging the gap between resilience and cascading analysis.
Yeah, hello, good morning, everybody. I hope you can see my screen. My name is Matthias Nobles. I'm a PhD student at the University of Manchester Center for Doctor Training in Power Networks. And my talk is about bridging the gap between resilience and cascading analysis. So events from last year, from 2019, actually August 2019, show us why this is an important thing to look at. And we had, like in the UK, we had a huge blackout in 2019. And basically several things coincided. We had a lightning strike, we had a technical fault at the wind farm, we had a technical fault at the gas power plant, and there was some like malfunctioning of distributed generation, as well as the involvement of renewables. And all of these things coincided, unfortunately, on this day, and it led to a huge loss of power. I think 5% of power was lost in the UK. Plus, and that's kind of important for cascading failures, is it wasn't just restricted to the loss of power, but it also spread into other infrastructure. So we had a loss of transport, hospitals were affected, water pumping stations were affected. So it's a huge impact, and it affects lots and lots of different things. Experience tells us that we need to look at these resilience events, and resilience events are events that don't happen very, very often, but if they happen, they are very severe. And in order to either assess or enhance these types of events, we really need to look at this in a multi-phase approach. It starts with the long-term planning, so then transmission expansion, for example, then the short-term control, then it's the event itself and looking at the mechanisms, usually the protection system that is involved in these cascading failures, how is this working? And afterwards is the restoration of the network. And last but not least, we also need to adapt. We need to learn from the event and we need to make improvements so the same things can't happen again. But because these events are so rare, we really need is a combination of data and simulations. So what we are doing at the moment is, so we are thinking like especially like the event phase is crucial for resilience assessment and enhancement, and understanding for what is happening during the event. So while the cascading failure is spreading, understanding of this is very, very important. So we developed a dedicated model for this, for cascading failures. And whilst there are lots and lots of cascading failure models out there already in the literature, we've specifically designed one for resilience analysis. And as such, it needs to fulfill some specific requirements. For example, it needs to fit and be integratable into established frameworks and methodologies. For example, like restoration methodologies or planning frameworks, and it really has to link with these to be easily integratable. Such a model needs to be very stable for large contingencies and extreme network conditions, exactly the kinds of things that happen during these resilience events. A model needs to be thoroughly validated, using real data, using historic outage statistics, and also needs to be computationally fast. And so we've developed this model specifically with these aspects, and we've now also made it open source and available via GitHub, so other researchers can use our model. And we're already very happy that some research in the field of restoration or transmission planning are using our model and trying to link everything together. The other aspect is we need to feed our simulations with real data. And what I'm looking here at is a basic data. And this is now looking at data that triggers these kind of events. We're also doing some other works on the restoration and the actual propagation of these events, but this data now for the triggering of these events. And this basically in the figure is a summary of all power cuts that occurred in the UK in 2020. And it's a very unique database. We built it from live outage reports from the DNOs. And it's a very comprehensive database as well, because it doesn't only tell us exactly how many events there are, how many power cuts there are, it tells us when they occur, how long they were, and also where they are. So it's a very, very good database. And already from this simple graphic here, we can see lots of interesting things. We can, for example, see all like the storms that happened in the UK and how they led to a massive increase in power cuts in the UK. We can also actually see the impact of COVID. And because we see during the first lockdown, there was actually a decrease in power cuts, although some media reports at that time warned that there would be a higher risk of blackouts during the pandemic. So there's a lot we can do from this data. And we can do some simple statistics with this. And this is just very, very preliminary already. We can match, for example, the number of outages with the electricity demand, and you can see that a higher demand leads to more power outages. We can map it, and you can see it on the right, we can map it with wind warnings issued by the Met Office, and we see that on days with a wind warning, we have a higher risk of power cuts, and we see that during the lockdown, we had a decreased risk of power cuts. And we are continuously doing more analysis with this data. And at the moment, we're doing some very interesting work where we look at where we map the power cuts with the local weather. And we also include social metrics like the level of urbanization or the level of deprivation in the area, and find correlations between these things. So to conclude, so the worst events in terms of power cuts usually happen when multiple things come together and when they also have an impact on infrastructure beyond just the electricity supply. And what we really need is a multi-phase assessment or a multi-phase approach for the assessment and enhancement of resilience. And because these events are so rare, we need to combine real data with simulations. And once again, I just want to mention, like, we've made our model like available for everybody. So if everybody wants to use it or is interested, please do get in touch. So that's all I wanted to talk about. Are there any questions?
Actually, I've got a question for you. So how do you think your cascading analysis model will be able to inform the power system protection and control?
Well, one thing that our model does, it tells us exactly which kind of protection mechanisms are involved in the spreading of the event. So is it like, is it under voltage things, is it under over frequency things? So it tells us, and I mean, it's just a simulation, it's just a model, but it tells us, it gives us a good thing, which tells us what are the mechanisms that that are important in the spreading. And it might also tell us like how we can play with the settings. For example, could we allow some under voltage or some under frequency at certain buses? And it can advise us on that. So in this way, we can, for example, inform protection mechanisms.
Okay, thank you very much. Next, I would like to welcome Professor Richard Wilden to introduce offshore renewables.
Hello, everyone. Let me just screen share. Hi, so my name is Richard Wilden. I'm one of the co-directors of the Supergen ORE Hub, and I'm just going to very briefly on this one slide tell you a bit more about the Offshore Renewable Energy Hub before introducing two of our ECRs to talk about their areas of activity. So we cover, within the hub and the broader community, we cover offshore wind, wave and tidal energy. And it's everything from the electrical connections to the foundations, all the way through to the atmospheric flows that drive the blades or the composite materials, etc. So I just introduce you actually to this little graphic at the bottom of the screen here. This is something that's quite nice. This is our research landscape. You can find it on our website down here. And what you can do is you can have a play with the kind of things we do. And this is a wave energy device, different wave energy devices, some wind farms in the background. And this is some sort of tidal stream turbine farms on the seabed here. And it's an interactive tool on our website, and you can sort of click on things and you can see, sort of what the current status of research activity is in that area, and what's going on within the hub and the wider community. So the hub itself is a partnership between 10 universities. Plymouth is the lead university, and 9 other universities throughout the rest of the United Kingdom. We've got a core research program and a flexible funded research program. The total fund value is about 9 million. Well, the total hub is funded to a total value of about £9 million. We've got various networking activities and assembly events, and the ECR network, of course, is a key part of that. And we've currently got about 150 ECRs involved in the ECR network. With the ECR network, we do various things, masterclasses, workshops, different sort of training events, but actually we also run an ECR flexible fund, which enables the ECRs to sort of bid for small amounts of money to try and progress their sort of research type activity. So lots of other stuff going on, all the normal things, informing government and interacting with industry, etc. I won't say anything more about that in the interest of time, I think. So I think if I stop sharing my screen, I'm probably going to get these in the wrong order, but I think I should introduce Sam Scott next, who's from the University of Bristol, and is going to tell us more about his research activities, and I think the wider activities going on in that area. So.
Hey everyone, this is Sam Scott here. Just wondering, can you see my screen?
Yes.
Yeah.
I'm just going to full screen the presentation. That's probably on the wrong side now, isn't it?
If you click the display setting, yep. Okay, there we go.
Is that better? Great. Cool. So, hi everyone, my name is Sam Scott. I'm a PhD researcher at the University of Bristol. And today I'm kind of speaking instead of my supervisor, Dr. Terence McCourt, who unfortunately can't make it today. But the kind of main aim of this talk is to give an overview of the WindBlade Research Hub, the capabilities, and hopefully kind of incentivize some collaboration. So the WindBlade Research Hub is a partnership between the University of Bristol and the ORE Catapult. And the main mission really is to develop larger, more efficient wind turbine blades that harness more energy from the wind. So this has kind of sponsored a number of PhDs and also staff joining the university. My PhD was one of these. And really there's a wide array of capabilities under the kind of umbrella of this research hub. So ranging from leading edge erosion research to full scale blade fatigue and ultimate load testing through to CFD, additive manufacturing. My research is highlighted in blue, which is on kind of integrated aerostructural design and optimization of the blades. But to expand on that slide a bit more graphically, like I said, there's a full-scale test tool up at the ORE Catapult. So this is a 100-meter blade test tool, and they're regularly doing fatigue and ultimate testing for OEMs. Then there's also a lot of research going on in rain erosion. So as we know, leading edge erosion of blades is a big problem because it's kind of causing a wearing down, which is significantly reducing the aerodynamic performance, and quite a lot quicker than everyone expected. So there's a rain erosion test rig, which basically does accelerated testing on leading edge coating samples. And there's a lot of work going on trying to predict the lifetimes of these coatings more accurately. There's also work on non-destructive testing and kind of looking to include these efficient truss designs in wind turbine blade structures. And to kind of expand a little bit more on my own research. So my PhD has been on multidisciplinary optimization of mainly the blades and with a kind of aeroelastic view to improve performance. So the tool that I've been using is one that's been developed in-house at the University of Bristol, which is known as ATOM. It stands for Aeroelastic Turbine Optimization Methods. And so really this tool, ATOM, can do a lot of things. And it can run through the whole analysis loop in an automated fashion. So starting from some blade and tower properties, for example, it can pre-process those into beams. It can then use those to run simulations according to the design standards. And then you can post-process those simulation results to, for example, understand strength, buckling, fatigue. You can also pull out annual energy production and also compute cost of energy. And then you can kind of close that analysis loop to do optimization. You can allow an optimizer to vary variables such as the chord length, the twist, the blade length, and with the aim to minimize, for example, cost of energy or blade mass. And so it's a really kind of vast platform with a lot of capability. And we kind of think that it's prime for collaboration. We've already done a little bit of that already. So some examples of previous collaborations include code-to-code validation. We've also tried out blades with some new sustainable composites, such as flax composites to replace glass. But really, we're kind of open to new suggestions for how we might offer the use of this platform to the wider research community. So some ideas that it might be including like investigating different controller performances, or if simply someone's starting out on a project and they need some details of blades or tower, then I mean we've already got a lot of the standard research models already kind of inbuilt. So that's something we'd be happy to provide and happy to learn about what other people's projects are. So to finish up, there's a couple of email addresses at the top, mine and my supervisors, Dr. Terence McCourt, and then two of the kind of main research leads under the hub, which is Professor Paul Weaver and Dr. Alberto Pereira. So that's all from me. Thank you very much for listening. I'll be happy to take any questions.
Do we have any questions? Sam, can I just ask about the use of these models in terms of engineering calculations? Because when we do optimization things, we always sort of, in the academic environment, we tend to just focus on one thing to optimize. But actually, I mean, these turbine blades are optimized. The design cases that need to be considered are absolutely huge. I mean, do you do any work with unsteady loading cases and that sort of thing?
Yeah, absolutely. So in Atom, the software I mentioned earlier, we can perform full aero servo elastic design load cases as you might in DMV bladed software. Yeah, so the full kind of unsteady aerodynamics, turbulent wind fields, tower shadow, wind shear. So yeah. We've also got non-linear blade, so non-linear beam modeling capabilities for the blade. It's specifically like, well, that's very relevant for kind of large multi-megawatt blades that we're interested in now.
Yeah, exactly. For commercial scale device. We've got a question here from Anita about are your results fed into the turbine manufacturing industry like Siemens and Hull? And I guess, Sam, you want to answer that?
Are your results fed in? So we've not actually had any partnership with Siemens, but at the University of Bristol, we've got quite a few. Well, we've had and we've got one at the minute project going on with Vestas. Who else is there?
I think
mainly Vestas actually, not Siemens, but yeah.
I think it's worth painting a wider picture that, of course, there's the Supergen and there's the ORE catapult as well. And actually, I mean, a lot of the activity in Bristol that you're involved with, Sam, is actually with the ORE catapult. And there's also a prosperity partnership that involves Siemens and Hull back through the Supergen ORE as well. So there's actually a whole mix of different programs operating in this area and crossovers to the big manufacturers as well.
Mm-hmm.
Okay, we better leave it there. Thank you very much, Sam.
Thank you.
Can I now introduce the second speaker for ORE Supergen, which is Dr. Pablo Oro, who's at the University of Manchester.
Hello, everyone. It seems I can't share because I'm
quite quiet.
Can you make me co-host, please?
You should be able to share now, Pablo.
Now I am, yes. Okay. Can you see the first slide?
Yes, you can. Yes.
Yeah, great. So my name is Pablo Oro. I am a Dave Kathleen Lorenzo Fellow at the University of Manchester. And I work on fluid mechanics and especially understanding the aerodynamics of wind and tidal turbines and how they're going to be integrated into the environment. But instead of talking to you about what I do, I will bring a question, which is how we are going to supply renewable energy to remote communities and islands, and whether hydrokinetic turbines are a potential solution to that. So these regions are isolated geographically. So here I put two pictures of Philippines and Vanuatu, because these archipelagos have hundreds of islands, and not all of them are connected to the main grid. So the population living there, they don't have a constant supply of energy. And what this brings is complex socioeconomic situations. So it is well known that not having access to a constant supply of electricity then is a proxy for poverty, for not having a good education, and so on. So there is a need, and there should be a commitment to provide renewable energy to these populations. Most of them are off-grid, as I said, so they rely on burning diesel, which is high cost and is also tricky because they need to get the supply either by planes or by boats, and it's challenging. So whether the resource from the river or from the movement of the sea flows, then could be a solution here. But normally these regions, they have a low resource. So they have velocities of about 1 to 1.5 meters per second. So technology we are developing now in terms of hydrokinetic turbines might not be suitable to these locations. But these are the challenges, and what are the opportunities? So we know that most of the people living in these regions do live near seas or river because it's a good way for transportation and to get food. And they have a low energy demand, so they don't require a huge power to fulfill their energy demands as we do in Europe or in the US. And if we do bring renewable energy to these places, then we can just change the way of living for them. They can do cooking and heating and cooling, and we can improve their health and the quality. So there is a lot of gain here. So when we talk about hydrokinetic turbines, a simple description is just thinking about wind turbines, but below water. So we have mainly 3 different designs. The first one is being the vertical axis Darrieus rotor. So the advantage of these turbines is because they have a low rotational velocity. They cut in velocity, so this means when the turbine starts to produce energy is relatively low. They are omnidirectional, so this means that the device doesn't need to jaw to align with the flow. It just it operates regardless of the flow direction, and they have a simple blade geometry, so they are very easy to manufacture. The problem we have with them is that the power conversion rates are lower compared to horizontal axis turbines because they have been underfunded and therefore underdeveloped. On the other hand, what we have is the 3-bladed or the 2-bladed horizontal axis turbines, which is what we see in onshore and offshore wind. And the advantage of these ones is that the power conversion rates are very high. You can see that they can reach up to 0.5, sorry, because they are mature technology that have been developed for, I think, more than 30 years now. The issues they have is the rotational velocity is pretty high. They also need high velocities to start producing power or energy, and they have a complex blade geometry, which means we need to have very specific facilities to generate them. So we need to figure out what axis, rotational axis best, but also whether we are going to deploy the turbines in a floating platform, because the advantage of this is that they have an easy accessibility and therefore maintenance, and they don't have a lot of impact on the benthic species. So these are the species at the bottom of the sea or the river, and they also bring more power generation because the power is proportional to the cube of velocities, and the velocities are higher near the free surface. On the other hand, what we have is bottom fixed turbines. So these turbines instead, they have a heavy foundation, so they can be placed at the bottom and they don't move. So for the floating platforms, we have moorings, so cables, and those are quite dynamic and influenced by the waves, but we don't have that in bottom fixed devices. And they also have lower loads because loads are proportional to the cube or to the square of velocities, and no visual impact. So if we are in Philippines in a touristic place, then bottom fixed turbines won't change anything in terms of the visual impact. But the main problem that we are working on for the last 2 years, we have had two projects with university, from one university in Colombia and another one in Brazil, is that horizontal axis turbines rotate at very high rotational speeds and they require high cutting velocities. So the main problem with this is the risk of collision with fish. Even though we have seen that that risk is low, then it might not be the best place to locate in a region that is environmentally sensitive. So some work we have been doing over the last few years is on vertical axis turbines, especially trying to improve the performance through a better design. We are not looking at peak performance, so power coefficient. So we are not aiming to produce a lot of energy in a given amount of time, but instead we want to produce a more constant energy output through a larger amount of time, if possible, all the time, as it could be the case of rivers. And also to demonstrate that they are more suitable for environmentally sensitive areas, as we can have fish. So this is a video of some tests. Oh, I think it's not working. Okay, anyway, so these are some tests that we are doing at Cardiff University with one vertical axis turbine operating, and we have one fish swimming in the wake. And we are trying to demonstrate whether when the fish swim in the wake of the turbines, then the energy expenditure is lower, but also that there is almost no risk of collision, or at least if they collide with the blades, they don't die. Oops. So my last slide is just I've seen this document from IRENAS, which is about the roadmap for supplying renewable energy to islands. And what I see, Supergens, not just the ORE, but all of us, is to try to bring innovative solutions so we can provide low cost energy solutions for these regions. So we have here the one tidal turbine, we have wind turbines, solar panels, and then we can include batteries and so on. But we need to do this in a pretty cost-efficient manner. So I think that it's time for the change, and I welcome any questions. Thank you.
Okay, thank you, Pablo. Do we have any questions? Anything in the chat? I will, in the interest of time, I think I'm going to ask one question, Pablo, and then if anybody else has questions, if they pop them in the chat, then I'm sure Pablo can answer them there. It's a question and a comment actually about the importance of the interaction with the environment and not just pursuing sort of optimization and power maximization type goals. So, I mean, where do you see the sort of the interface and that sort of engineering and environmental research, and how can we better try and actually bring some of that sort of environmental impact type activity in the research activity we do for tidal specifically?
I think we need to do an evaluation of the available resource, and that's going to be different if we look at islands, because the tidal phases are not constant, so we don't have a tidal flow going through all the time. Whereas in rivers, we do have, and I think a pretty good application to that in terms of the optimization and the whole environment is what Kumar was talking about before in Bangladesh. They do have one hydropower station, but I don't think there are river turbines, and these are easy solutions that can be implemented. But then whether we need to optimize the functioning and the deployment and the economic costs and returns, then I think it's on a case basis.
Okay, yeah, that makes sense. All right. Thank you, Pablo. There's a couple of comments in the chat there, but I'm going to let you answer those in the chat if that's all right. Okay. So I think I'm now handing back to somebody else.
Okay, thank you much. Next, I would like to welcome Luke Jones from Super Solar Hub on his presentation of super hydrophobic anti-soiling coating for photovoltaic module covered glass.
Hi, yes, good morning. I'll just share the screen now. Can everyone see the screen okay?
Not yet.
Not yet.
It is a green button. So
Yeah, it says it's sharing.
oh, now I think
it's coming up.
Okay, yeah.
Yeah, there we go.
Okay. All right. Good morning, everyone. My name is Luke Jones, and I am a first-year PhD student at Loughborough University in partnership with the Centre of Renewable Energy Systems Technology, otherwise known as CREST. Today, I'd like to talk to you about my PhD project, which is the development of a hydrophobic anti-soiling coating for solar panel cover glass. So with the short time I have today, I hopefully would like to cover the following objectives. I'll start off with why this research is important, talk a little bit about the problem, and then finish up with the research I'm conducting to hopefully solve the issue. So out of the renewable energy sources, solar energy and PV technology has seen the most substantive growth year on year. As of 2019, the world is generating over 600 gigawatts of electricity from solar energy alone, and is predicted to reach 1 terawatt in the coming years. But bear in mind that these predictions were made before COVID-19. However, the latest data from IEA still shows that the growth of the solar PV energy in 2020 is greater than any other form of renewable energy, despite the impacts COVID-19 had on supply lines. Whilst this is all promising news for the outlook of solar energy and PV technology, the industry faces a huge problem that needs to be addressed, and that problem is soiling. As you can see from the slide, soiling is buildup of foreign particulates and residue on the surface of the solar panel cover glass. The accumulation of this dust or plant debris, biological material, and other particulates attenuate the light on the surface of plain glass covers and can lead to reduced light transmittance from anywhere between 5 to 50% in the first month alone. This could even go as far as 100% depending on the weather and the maintenance schedule. This leads to massive reductions in output power and therefore increased economic losses, maintenance costs, etc. While soiling is a known problem, the cause of the problem is highly complex. Here, I have listed some of the factors that influence the effects of soiling. It is important to note that these factors, as they are important to keep in mind when attempting to solve the problem. One method proposed with dealing with this soiling is to apply a hydrophobic coating to the surface of the cover glass. These effects can be clearly seen in the work conducted by my colleagues at CREST with our partners in Colorado State University. During sudden snowfall that day in Colorado, you can clearly see the effects of the hydrophobic coating, with the highlighted hydrophobic panel being the only one not covered. Additionally, if you look at the right image, you can also see the difference in residue left by the snow once it has melted away. So this is where my project comes in. Currently, I'm working to develop a hydrophobic coating that can be applied to the surface of these solar panel cover glasses. The aim is to work with a polymeric coating, possibly fluoropolymer based, which can be applied to the cover glass manufacture or later during its operation. The development process has already begun, but effectively, I am currently using my experience and expertise in surface characterization to really take a deep dive into existing coating chemistry and morphology and learn as much as I can. These techniques include X-ray photon electrospectroscopy, infrared, and electron microscopy. After this, I actually aim to work backwards by putting these coatings through accelerating aging experimentation, such as UV and damp heat, and identify their degradation mechanisms. Further information of these mechanisms can be found in my abstract submitted to the IEE PVSC conference this year. Once I've researched further into the degradation mechanism, I will begin to formulate chemistries to tackle the larger issues that face hydrophobic coatings and hopefully develop a commercially viable, environmentally durable coating. Thank you very much. And are there any questions?
Okay, any questions? Oh, there's a question from John. So have you considered using self-assembled mono layers for these?
Yes, so that is one of the potentials that I am currently considering. really, the current stage that I am at, since I've only really been working on this for a few months now, is more into the degradation mechanism and what are the issues facing the hydrophobic coatings currently on offer on the market.
Okay, thank you. There's another question from James, but I'm a little bit conscious about time. So, so Luke, maybe if you can type in your answer in the chat box, that'd be great.
Yeah, that's fine.
Okay, I'll welcome the next speaker, Jonathan Harwell, on the presentation of new designs for cheaper and more efficient thin film solar cells.
Right, hi there. So can you guys all see my screen?
Yes.
Right, excellent. So right, okay, I'm very conscious of time, so I'll be very quick. So basically, my research works on looking at new designs for thin film solar cells. So very first thing I'll do is, what are thin film solar cells? So normal solar cells are like silicon wafers and that sort of thing. They're rigid, they're expensive to produce. And basically, the vision we have is basically you'll have inks which you can basically print and make a solar wallpaper, or like a flexible solar cell which you can roll up like a newspaper, and they're all very cheap. And so there's lots of very cool and exciting technologies with this. And so one of the issues I'm going to address is basically getting light into the solar cell. And so what do I mean by that? So this is basically a very simplified design of a solar cell. You have an absorber sandwiched between two metal contacts. One collects electrons, the other one collects positive charge, which is called holes. And there's immediately a problem here, in that basically, like if you've got metal on either side of your absorber, light can't get into your solar cell, which isn't very useful for a solar cell. So what silicon solar cells have used in the past is basically you make, instead of having a solid top contact, you have a grid. And you can see this on the right with what a silicon solar cell looks like. And the separation of these contacts, you want them to be as far apart as possible, but basically it's a optimization between how far can the electrons travel versus how much light do you want to let in. So a nicer solution is basically, instead of using that, you use a transparent conductor, which is not this is a material called ITO, is the most commonly used. This is something which is both transparent and conducts electricity, but these are rare, expensive, and just nowhere near as good as using metals in general. So the solution I'm working on is a back contact device. Basically, so instead of having your grid on the top, you have alternating fingers of the two contacts, and so long as the separation distance is the same as in the front contact, you can get good charge collection. And so in silicon solar cells, this has actually become in fairly recently, where basically if you look on the left, you can see this is what a normal silicon solar cell looks like, and on the right, you have a back contact solar cell. So it's letting much more light in, and it's so much more efficient. However, for thin film solar cells, there's a catch in that the separation of these contacts needs to be a lot smaller, like 500 nanometers small, which is about the size of a coronavirus. So and it costs you in the thousands of pounds per square centimeter to make something like that commercially, if you're doing it for a thin film solar cell. So there's lots of advantages to back contact solar cells other than just efficiency. You can do you can make a recyclable device, or you can put like passivation or anti-reflection structures on it. I'll skip over this because we're running short on time. And basically, so my work is on trying to find ways to make these structures as cheaply as possible. So as I said, like if you want to make a thin film solar cell with a back contact, you need structures which are in the order of like 500 nanometers across, which is very expensive. So I try and let nature do it for me. And so this here, I've got basically that one of the ways we do it is we use the self-assembly of polystyrene nanospheres, which you can just buy, and they will, and if you deposit them in exactly the right way, then you can form a perfectly close packed layer, which you can then use as a mask to make these honeycombs, which are about 500 nanometers across. And so this is one of the ways we are looking at trying to make them cheaply. And then once we have this structure, you can basically copy it using a method called nanoimprint lithography. Where basically you have a thermopolymer and you've made a stamp using the nanospheres, and then you basically stamp it into your polymer, and then you can reproduce the structures, and then you get the exact things which you need. And so you can see here, this is the sort of quality of the structures you can make, and you can even make, I call them nano mushrooms, where you have a very thin stalk and a hemisphere on top. And these have all got lots of potential applications for making efficient and cheap solar cells. So my vision for this over the course of my EPSRC funded project is to basically make efficient back contact solar cells and then scale these things down to use cheaper and cheaper setups. So like as I said, like initially to make the master structures, people often use like a £2 million electron beam lithography system, and then move on to a thermal nanoimprint system, which costs you in the order of 300K. And basically, I'm going to try and scale this down to the end. Maybe can you just do it using a t-shirt press, which is a cost you about £100. And the same thing like way depositing metals. Normally you use a thermal evaporator, which is about 200K. And can you do this with an electroplating setup, which would cost you in the hundreds of pounds? So basically I want to make efficient, reliable cells, which almost anyone can make in their back garage. That's a power through my project, but thank you very much for listening, and I'll take any questions. Okay.
Okay. Yep, I've got a question from Amruta. So is this copper electrocoating? If yes, is there any effect on diffusion of Cu on thin film solar cells?
Yes, we do use copper. We can also use other metals such as nickel and gold. Diffusion is an issue. I've massively simplified these structures. So we usually, after we have deposited the copper or the nickel, then we will coat them with an oxide layer as well, which prevents diffusion and also provides charge selectivity. So that's one of the avenues I'm researching. But copper in general, certainly with perovskite solar cells, which is one of the things I work on, copper diffusion is much less of a problem than say if you use gold, for instance. Okay.
Okay. Thank you very much, John.
Thank you. All right, so I'll stop sharing now. Right.
And thank you very, very much for everyone to join today's Cross-Hub webinar. And if you have any questions for any of the speakers, can I ask you to email the representative of each hubs? And I would like to thank all the speakers for today and also all the representative from the Supergen hubs. And also I'd like to especially thank Dr. Angela Fivga for coordinating today's event. Thank you much, and looking forward to see you in our future events.